So if we look at this example where we have a root of 4, we know that we need to keep in mind that this is a binary search tree, meaning that for any node in here, the left subtree node values must be less than that node, and the right subtree values of a certain node must be greater than whatever node we're at. So how we're going to approach inserting a value, let's say we're trying to insert 5, we're going to start at the root, and we're going to ask the question to 4, are you empty? And we realize it's not empty, so then we'll move on and start trying to compare this 4, the node value here, to the value we're trying to insert. And when we do that, we realize that 5 is greater than 4, so then we know that we just have to go to the right subtree, and we can kind of get more details, right? So then we go to this node right here, 7, and we compare 7 to 5, or we do the same process, right? We go ahead and say, is 7 null? It's not null, and now we can compare, right? So then we try to compare and we realize that 7 is greater than 5, so we try to go to 7's left subtree, but we realize we hit null. And once we hit null, this is basically our way of understanding that we'll go ahead and we can create this node. So what I'll do is create the node. And now I have my node, but I need to connect it back up here. So what's going to happen is that I'm going to assign whatever this pointer is to this new node we created. So now it'll be pointing at 5. So we just return this address back over here to whatever this node's address is. So now, I mean, what it really looks like now is just its left pointer now has 5. That's the idea of the algorithm, and yeah, now we kind of jump into the steps of how to code it up. So the way we're going to start this up is that we're going to first check if my root is empty. So we'll say if my root is none, then we know that we can actually just return the new node. So we'll say return tree node, and we're going to pass in that value that we're trying to insert. Otherwise, if we made it this far, then we need to figure out which side of the tree I need to go, either the left or right subtree. So we're going to make comparisons. So if my root dot value is less than the value we're trying to insert, then that means I need to go to the right subtree to go ahead and place that value. So I'm going to say root dot right will be assigned to, we're going to call the function again, and we're going to traverse to the right node, so root.right, and then we're going to pass in the value we're trying to insert. Else, this is the case when our root value is greater than our value. So if that is the case, then we know that we need to go to the left subtree. So we'll say root.left will be assigned to whatever pointer comes back from this insert into binary search tree. And we're going to say root.left because we're going to go that direction, and then we're going to pass in the value. And we don't really have to worry about when they're equal because the question specifically says that we won't ever get duplicate values, so it's not really something we have to cover. And then once we're done here, we just need to return the node back up. So we're going to say return node, or rather root. And this should be good, so let's test this out. So for the time complexity, it's going to be big O of n, where n is the number of nodes in our tree. And the reason why it's that is because let's say we have this tree on the left side, right? It's skewed left, and we try to insert 1. We can do that by traversing down, and then we probably put it down here. But what happens here is that we have to go through 4, and then I have to go to 3, and then I have to go to 2. So I have to visit every single node within that tree. So then that's why it's going to be big O of n. And then as for space, we are using recursion. So the stack frames or the recursion will scale based off the number of nodes in the event we had a skewed tree like this, right? So space is also going to be big O of n as well.